Hello, my name is Sina, and I'm going to present our paper titled Locality-based test selection for autonomous agents. The main goal of us in this paper is to improve safety in smart cities for communicating and connected intelligent vehicles. To reach this goal in our project Safe Smart, we have a couple of sub-projects and subgroups. One group in this project works in decision and control. One group works in communication and network. One group works in sensing and localization. And we are here in testing and integration part, working on testing safety for communicating vehicles. The main message of us in this work is that locality-based filters improves test efficiency of autonomous agents. So in this presentation, I will go through different parts of this message one by one. First, I will talk about our point of view about autonomous agents. Then I will talk about testing these systems and automating the testing process for them. Then I will discuss how locality-based filtering can be applied on the testing process. And at the end, I will talk about the efficiency of tests by using this methodology. In our paper, each autonomous agent has one starting point and one end point, and one planned path to reach from the starting point to the end point. The autonomous agents move in a two-dimensional grid, and from each autonomous agent, it is required to avoid collisions with other agents in necessary cases. For example, at some points, following the planned path for the agents can lead to collisions with the other agents. So in such cases, it is required from the agents to change their move to a move other than the planned paths to avoid the possible collisions with the other agents. That was our point of view about the autonomous agents. But how can we go for testing these systems? From testing the autonomous agents in this work, we want to check that in some situations any collision can happen for the agents or not. For doing that, we have a black box testing approach. Since we know that in many cases we do not have access to the source code, and as a result we cannot analyze it. For creating the test suite, we consider having automated test suites instead of manual one, and for doing that we are utilizing randomly generated test inputs. As an example, in our case we can generate this randomly generated input and give it to the system under test for execution. After execution, we can monitor the output. If any collision is detected in the output, we can say that we found a failure. Otherwise, we can repeat the same process for some other randomly generated inputs and make a decision after that. In generating random test inputs, one question to answer is that how should we define randomness in the data generation process? In our case, we want to generate a path with length L. We can do that by picking a random start position and then select L random actions from the list left, right, up, and down. By doing that, we will have a random path as well. However, when we generate paths by having this method, we will see that the generated paths are compact and isolated, which is not suitable for the purpose of our testing. We want to generate paths for checking that in different interactions of the agents, the collision avoidance mechanism of them works well. However, when the agents are totally isolated with each other, this collision avoidance mechanism will not be tested well anymore. In fact, there is a mathematical reason behind having a compact paths by having this method. Supposing that we want to generate a path with length L, which L is a very large number. Since we have a random selection from the list left, right, up, and down, at the end we expect the number of lefts, rights, up, and downs in the target selected set would be the same. Which means that since the number of going to left would be the same number of going to the right, horizontally the starting point and the end point should be the same. And similarly, since the number of going to up would be the same as going to down, vertically the distance between the starting position and end position would be the same. In other words, we can say that starting position would be the same as end position when L is a very large number. When L is not a very large number, start position and end position would not be necessarily the same position, but we expect them to be very close to each other, which result in the isolated and compact paths shown in this figure. To resolve the compactness problem of paths that we had in data generation method A, we can try another way of defining randomness in data generation process. In method B, we pick a random start position A, and then we pick another random end position B as an endpoint, which can be reachable with L moves from the A, and then pick a random L horizontal and vertical moves from A to B. At the first glance, method B may look like the same as method A, but since we give freedom to the endpoint over here to be far from the starting point, in the data generation examples, by having method B, we can see that the compactness problem is resolved. And in our paper, we use method B for generating test inputs. So far, our point of view regarding autonomous agents and the way of testing and automating the testing process for these systems is covered. But can we guide random testing towards more interesting test cases or not? In testing autonomous agents, each test execution or simulation can be very time-consuming and costly. So when we are using randomly generated inputs that can contain many uninteresting test cases, executing all of the randomly generated inputs can lead to losing so much time in the testing process. But if we can define a criterion for evaluating test inputs and understanding which test inputs are interesting and which are not, we can only go for executing test cases for interesting ones and just discard the not interesting ones. For defining such a criterion, we can use domain knowledge. In our case, the distance of agents and the path intersections of agents can be used as two factors for defining such a criterion. As an example, if the test input contain two agents that their distance is 1 at some time, we can say that this test input is interesting and we can go for testing that. As an example, in this generated paths, at time 0, the path green and yellow have the distance 1. So based on this criterion, this test input is interesting and we will use that in the test execution part. For formalizing the test selection criterion constraints, we propose this simple domain-specific language. In this DSL, we consider satisfaction of different conditions, which we have two conditions, in different areas, which currently we have two areas. And also we consider composition of different constraints as well. We also proposed the domain-specific language semantics in detail in the paper that can be used for analyzing, composing, and comparing different constraints, and also it can be used for extending this DSL in other domains and other domain-specific languages. As an example of test selection constraint definition by using our DSL, in square 2 cont 3 requires that in the test input there must be 3 agents in a square with side length 2 at one particular time. So if this is the generated input and this is the constraint selection criterion, since we can find a square with side length 2 which contains 3 agents at the same time, we can say that based on this constraint, this test input is an interesting test input. In circle 1 intersection 1, 2 is another test selection constraint which requires that in the test input there must be one path intersection of 2 agents in a circle with radius 1. So in the given test input, since we can find a circle with radius 1, the area Z2, which contains one intersection of 2 agents, we can say that based on this criterion, this test input is also interesting. In square 2 cont 4 is another criterion which requires that in the test input there must be 4 agents in a square with side length 2 at one particular time. Since in the given test input we cannot find the square and any square with side length 2 containing 4 agents, we can say that based on this constraint criterion, this test input is not an interesting test case. So far, we provided our point of view regarding autonomous agents, the way of testing and automating the testing process for them, and making the test selection more guided to the challenging ones by defining locality-based filtering criteria. But does our approach make the testing process more efficient? And if yes, is the improvement significant or not? To answer this question, we design and conduct an experiment. In this experiment, we have 3 filters, filter F1, F2, and F3. Our system under test has a 100 by 100 grid, including 5 agents, and each agent has 5 steps to go. The implementation of movement of the agents is in this way. We first check all of the available positions, then try to move all of the agents one step sequentially. Then if the next position is available for one agent, that agent will go for that. Otherwise, it just waits. As an example of our implementation, suppose that we have 3 agents A1, A2, and A3 with the planned path in this figure. Since the next position for all of the 3 agents are available, they just go for that. Then they will check the next position again. Since the next position for blue agent is not available, it just waits. But since the next position for green and yellow, green and red agents are available, they go for that. And as it can be seen from this implementation, we have the possibility for collision of the agents. In this time, the next position for all of the agents are available, and the agents will go for that. However, we can see that in the next time we will have a collision between the agent red and green. To conduct our experiment, we use the tool QuickCheck. QuickCheck has many random data generators. For example, we can generate a random integer or a random integer between two numbers, or pick a random element from the given list, or we can generate a random sublist from the given list. We can also compose different generators by QuickCheck to make a new generator. For example, having the generator G, we can generate a random list of elements. Which each element of that is generated by the generator G. QuickCheck is mostly used for model-based and property-based testing. It has also one feature for filtering test cases, which we use in our experiment. One of the features of QuickCheck is that when it reaches a failed test input, it tries to shrink the failed test input as much as possible based on its own internal heuristics. The most shrunk test case would be useful in locating the possible location of bug in the source code. When QuickCheck tries to shrink the test input, some of the attempts to make a smaller or more shrunk test case would be successful, which is called as successful shrink steps, but some of the attempts to shrink the test input would be failed, which we call them failed shrink steps. And when we have a test filter in QuickCheck, we can use it in a shrinking process as well. So in shrinking process, we also check that the modified input is interesting or not. If it is an interesting modification, we will go for shrinking that. Otherwise, we just discard it. From our experiment, we want to answer two research questions. First, we want to check whether our methodology will lead to faster detection of fault in the system or not. And for doing that, we calculate the number of test executions until reaching the failure in the system. And our second research question is that whether our methodology will lead to less number of shrink steps to find the most shrunk test case or not. And of course, for doing that, we calculate the number of successful and failed shrink steps. To answer the first question, we calculated the number of executed and discarded cases up to detecting the failure. And we repeated the same process and gathered the results, and we will use that in the statistical test. But in average, we can see that to find the first failure with no filter, we generate around 450 cases and we execute all of them. But when we have, for example, filter 1, we discard about 300 of them and we only execute 150 cases. By doing that, we save so much time in avoiding to execute unnecessary or uninteresting test cases. We have the same procedure in filter 2 and filter 3 as well. We discard a big portion of the generated test cases and we only execute a small portion of that, and we find the failure after that. To answer the second research question, we calculate the number of successful and failed shrink steps in our experiment by the tool QuickCheck. We do that up to detecting the first failed test case or the failure. We repeat the same process and calculate and gather the results. On average, we can see that more or less the number of successful shrink steps in the case of having no filter and having filter 1, 2, or 3 is the same. but we can see a slight reduction in the number of failed shrink steps when we have filter 1 in comparison with having no filter. We even see less number of failed shrink steps in the case of having filter 2 and filter 3. We have already seen that in our experiment we had some improvements in the number of test executions and in the number of shrink steps. But to check whether the improvements are significant or not, we need to apply statistical tests on our data. Our alternative hypothesis in the statistical tests is that the number of results in the case of having no filter is greater than the results of having filters F1, F2, and F3. For doing our intended statistical test, we need to first check the normality of the data, and for doing that, we apply Shapiro-Wilk test on the data. And based on the result of this test, we choose the relevant statistical test to apply on our data. For the number of executed test cases, we can see that the p-values are less than 5% for all of the filters. So we can say that the number of test executions improved significantly by having the filters F1, F2, and F3. For the number of successful shrink steps, the p-values for F1 and F2 are greater than 5%. So we can say that with a good confidence level, we cannot say that the improvement is significant for filter F1 and F2, but we can say that with a good confidence level, filter F3 has significant improvements for our data. We applied the same U-test for the failed shrink steps data, and we can see that for all of the cases of filter 1, filter 2, and filter 3, the p-values are less than 5%. And as a result, we can say that our methodology of having filters improves the number of failed shrink steps significantly in comparison with having no filter. In this work, our main message was that using locality-based filters improves test efficiency of autonomous agents. So in this presentation, we talked about different parts of this message. First, we provided our point of view about autonomous agents, and then talked about how we can automate the testing process for such systems by generating random inputs. In our case, we generated random paths, and we also discussed how we can define locality-based filters for selecting interesting test cases. At the end, we evaluated our methodology by designing and conducting experiment and discussing the results. Thank you so much for your attention. If you have any questions, you can contact me with this email.